All right, so in this video, I want to walk through this particular practice problem that I had shown in class and given you guys some time to work on. And I want to emphasize that, like, maybe the way that, some of you were working through this problem was not wrong. Like, you may get to the right answer eventually, but there is maybe a way to speed things up. And so I wanted to walk through kind of how I would approach this problem, kind of taking into account some of the different things that we've learned about, say, stoichiometric ratios in gases and applying that here. But basically what's described here is a reaction of carbon disulfide and oxygen gas forming carbon dioxide and sulfur dioxide gas. So that balanced chemical equation is written up above, and as described in the scenario, we're basically going to run this reaction in like a closed container. So our container is 750 milliliters large, and initially container is like at room temperature, so 20.14 degrees Celsius. And at the start there, when we have this kind of room temperature reaction mixture, we actually don't have both of the reactants as they're described in this balanced equation. So initially we have, say, the oxygen gas that's in the gas phase and has a pressure of 1.05 atmospheres. But then instead of carbon disulfide gas, we have in fact liquid carbon disulfide. And the reason behind this is that, like, at room temperature, CS2 is actually a liquid. It's not above its boiling point and not in the gas phase. But so we start with that liquid CS2, 1.208 grams of it. And what we want to do is start the reaction. So to start the reaction, we actually heat the vessel up to a higher temperature. This causes the carbon disulfide to evaporate and go into the gas phase, and thus kind of kickstarts the reaction and starts getting it going. So there's a lot going on here in this scenario, but what I want us to find from this is what the total pressure will be of our entire reaction mixture after the reaction has occurred. We're making a couple assumptions here as far as like what goes on in this reaction. For one, the volume of the container that it's in is going to be constant. So it starts at 750 milliliters, it's going to end at 750 milliliters. That's going to stay the same. And then also the temperature of the reaction vessel will be held at that higher temperature, 138.63 degrees Celsius. But so, right, with this problem, there's a lot of moving pieces, a lot of different ways to approach it, but I want to show here kind of how I would most simplistically narrow down how to answer this question. Because, right, when we're asked here for the total pressure after the reaction is completed, there's a lot of, different questions kind of within that. It's really asking for, like, what is the theoretical yield of carbon dioxide or of sulfur dioxide? What is the excess reactant in this reaction? And taking all of those and adding them together, right, that will tell us then the total pressure of this mixture. But so to kind of get this started, right, the first thing that I'm gonna want to do is just to kind of get, like, I guess, a baseline as to where my different reactants and products are beginning. Right, I want to first find the pressure of each reactant before the reaction has begun, but after I've heated it up. So, right, this is just to kind of, I just give us an idea of like what exactly we're starting with our different reactants and putting that just in terms of pressure here. So for instance, for oxygen, we're told a few different things from the information given. We start with a pressure of 1.05 atmospheres of oxygen. However, that pressure is specifically at that lower temperature, 20.14 degrees Celsius. So if we want to find the pressure of the oxygen after it's been heated up to that higher temperature, right, we're going to need to use basically that rearrangement of the ideal gas law where N and V are going to be held constant, and thus P1 over T1 is equal to P2 over T2. So, right, this is just to relate, say, pressure and temperature changing in this scenario so that, right, if we have our P1 as 1.05 atmospheres, T1 as that lower temperature, and then T2 as that higher temperature, right, we kind of have all the pieces in here that we need to solve for P2. That would be like our pressure at the higher temperature. So setting that up here, right, I kind of already know pressure and temperature and things. I just need to convert my temperature into units of Kelvin in order for this ratio to work out. So, right, Again, plugging in like P1, T1, and T2, I can then solve for P2, which would be kind of that, higher temperature initial pressure of oxygen. And that gives me then 1.47 atmospheres for the O2. Now to keep track of things, I'm going to kind of like tabulate up here my different partial pressures for each of the different components in here, before the reaction, so initial, and then after the reaction as final. This is just to keep track of everything because we're going to see a lot of these numbers kind of jumping around. But so for O2, we'll say 1.47 atmospheres. And then for our products, we can just assume that they start at 0. So now carrying along here, right, we want to also find the pressure of the other reactant, CS2, initially. Now for CS2, we're not given a, starting pressure or anything like that. We're told like how much the CS2 weighs, along with things like the volume and the temperature of the CS2. So with that information, right, we can actually use the ideal gas law here. Say pressure is equal to nRT over V. For CS2, right, N is going to be found by taking 1.208 grams and converting that into moles using its molar mass. R is a constant. T is going to be the absolute temperature, again, at this higher temp after heating, so 411.78 Kelvin. And then V is just the volume in liters, so rather than 750 milliliters, we've got 0.75 liters. And so kind of evaluating that out, right, we have all of our different units and things checked out. So pressure should just be equal to 0.7148 atmospheres for that initial pressure of CS2. And so, right, again, this is just to kind of give us, I guess, like a baseline as to what we're actually starting with in terms of these different pressures, because we're going to use these pressures as they stand, right, in this kind of current format at the higher temperature to relate that to maybe each other's pressures. So, right, we kind of looked at in class how things like a balanced chemical equation could be used as like effectively like a mole ratio, but for atmospheres, for relating pressures of different substances. When we have these initial pressures right here, that's how we can kind of then use those mole ratios. So let's take a look at maybe what we would do next to answer this, right? Because what we effectively have here is like starting pressure of one reactant, starting pressure of another reactant. We want to find the total pressure, that is like the final pressures of each one of these different things at the end of this reaction. So what that kind of implies there with our two reactants going on, we're going to need to determine whichever is the limiting reactant and thus what the theoretical yield is from that limiting reactant. To get us started, I'm going to find, say, atmospheres of CO2 from all of the O2 reacting, as well as if all of the other reactant completely reacts, then how many atmospheres of CO2 could be formed from that. Now, I don't need to like necessarily go from like pressure of oxygen into moles of oxygen using the ideal gas law, and then use like the mole to mole ratio that we have in our chemical equation to get to moles of CO2, and then go back to say atmospheres of CO2, right? That's like one way to do it, but we can kind of like shortcut things and really just use like the 1.47 atmospheres of O2 that we started with, use that mole ratio from the balanced chemical equation that says 1 mole of CO2 for every 3 moles of O2. If we just apply that directly to the pressure, because these are in the same container, they have the same volume, the same temperature, right? Those things are being held constant. So really here with this like mole ratio, it's sort of like a pressure ratio for the two as well. And so I can just directly take my 1.47 atmospheres of O2, multiply it by 1 over 3 from the molar coefficients, and that gives me then 0.491 atmospheres of CO2. Doing the same thing for the CS2, we started with 0.7148 atmospheres of CS2. We can see that there's a 1-to-1 mole ratio from the balanced chemical equation, and so that should equate then to 0.7148 atmospheres of CO2. So these pressures of CO2 that we kind of predict from our different reactants, that's effectively the theoretical yield, right? Or the same kind of calculation that we would do to find the theoretical yield. In this case, the O2 produced less of the CO2, so that 0.491 atmospheres of CO2 is actually its theoretical yield. Additionally, because the O2 produced less, right? That makes O2 the limiting reactant. And so we know then that O2 at the end of this reaction should completely run out, which is to say then that the final pressure of O2 should be 0 atmospheres because again, it's limiting. All right, but so highlighted here, right, is how we can make that conversion between say one pressure and another pressure very directly, right? We don't actually need to go into PV equals nRT, solve for N, do all these other conversions and things with that, right? You can just use this direct mole-to-mole ratio as sort of a pressure to pressure ratio, right? It really does work that simply. This is again assuming that the two pieces of this, right, both the oxygen and the CO2, they're in the same container, meaning that they have the same volume and the same temperature between the two of them. Now carrying this on, right, we also want to find basically our theoretical yield of the other product, SO2. So we already know that O2 is the limiting reactant. I don't need to do like the what if scenario again. I can just take my 1.47 atmospheres of O2 that we started with and convert that into atmospheres of SO2, again using the mole-to-mole ratio and seeing 0.983 atmospheres of SO2 as the final pressure. All right, so we have like a bunch of different pieces now. It's all falling into place. So right, the final pressure that we need to find here is just the pressure of the excess CS2. So as one method to find, the amount of excess reactant remaining, what I like to do is basically start with your limiting reactant amount, so the 1.47 atmospheres of O2, and convert that into atmospheres of the excess reactant. So again, mole-to-mole ratio, find that 0.491 atmospheres of CS2, go with 1.47 atmospheres of O2. Now that doesn't mean that we have 0.491 atmospheres of CS2 left over. That just tells us how much of the CS2 gets used or is like needed for this reaction. And so what we can do is kind of take our initial amount of CS2, subtract out the amount that was used up. That tells us then how much is left. So we actually have 0.223 atmospheres of CS2 remaining at the end of this whole thing. All right, but so now we have, our full completed table here, right? All of my different final pressures are accounted for. And so all I need to do then is add those all together to get my total pressure, right? It's just according to Dalton's law of partial pressures, summing up the pieces of the mixture. And so using those values that we had before, right, the 0.223 atmospheres of CS2, 0 atmospheres of the limiting reactant O2, 0.491 atmospheres of CO2, 0.983 atmospheres of SO2, all of that added together should equal then 1.698 atmospheres in total. So right, again, this is just like one way to approach this problem. And I know it seems kind of drawn out because like I had to explain all of it, but I assure you that this is much more efficient and quick than maybe going through actually doing like a full PV equals nRT every time and all of that business, right? This is one way that we can kind of streamline things in approaching really complicated problems like this one. Like this is a pretty hard problem, and I won't say that I'll necessarily ask you something quite this complicated on an exam, but do think like somewhere in between maybe what you see right here and maybe some of the other examples that we do in class, right? There's a lot of moving pieces, but we want to kind of account for all of them, and the easiest way to do that is to kind of take our mole ratios that we see in the chemical equation and apply that to our partial pressures and things. So we can kind of use that here as a way to work between pressures as well. All right, but please let me know if you have any questions, and I'm always happy to help.